In this short video, I'll draw a proof of theorem 2.6 in the book. And here's the theorem. So we have two numbers, integers r and r is anywhere between 0 and n minus 1. And because and this theorem says that there exists an r regular graph on n vertices, if and only if at least one of r and n is even. So yes, r needs to be definitely in this range because the smallest degree a vertex can have is 0 and the largest degree the vertex can have is n minus 1. So yes, we want that. And let's prove this. So there's two directions. One is the direction that if there exists a graph, then r times n is even. And this follows immediately from this first theorem of graph theory. So if we add up all the degrees in a graph, then we get an even number, because if we add up all the degrees in a graph, we counted every edge exactly twice, once from each side of it. So r times n is exactly adding up all the degrees in an r regular graph on n vertices. So this number must be even to even have a chance to find a graph with these parameters. On the other hand, this theorem states that this is actually sufficient. And let's draw a picture. So draw n vertices, and I'm going to arrange them somewhat cyclically, like that, right? And I don't know how many there are, so dot, 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 like that. So degree 0, done, right? We can do degree 0. Degree 1, we only have to do if n is even. So if n is even, we can get degree 1 like always taking the exactly opposite vertex, like that. So here is for the even case, we can get degree 1 like that. So we want to use those exactly if r is odd. And now for all even numbers, all even r's, we can just put a cycle like that in there. So we can add 2 by adding this cycle. So this would be degree 3 with green and red combined, and it would be degree 2 with just green. So now, how do we get any higher? Well, look at this next one. So if we look at a vertex and connect it always to the neighbors that are 2 away, like so, and then do the same for every other vertex that's in between, we add 2 to each degree. So this way, if we combine blue and green, we get 4. If we combine blue, green, and red, we get 5. And again, important to note, red we can only do when n is even, but we only have to do it when n is even, because we only need red if we want an odd r. And we can play this game of jumping further. We can do, if we want to add 2 more, we just jump to the third from each one, like that. And always jump on, right? Here's the third. So if we combine black, green, and blue, we get 6. And if we add the red ones to it, if n is even, then we get 7. And this picture we can continue however long we want. So we always have to jump up to r over 2 distance to either side to get r and possibly, if we want an odd R, add the diagonals, like so. And the worst we ever do, of course, the most we can ever do is n minus 1, which would be the complete graph. And the complete graph, the n minus 1, of course, always works, because 1 of n and n minus 1 is even, so we're not breaking anything. And of course, the complete graph is n minus 1 regular. So this is the proof of this theorem.